presentation is Applications and Qualities of NDE Technologies for Bridge Deck Assessment, and it's by Dr. Glen Washer. Glen is a professor at University of Missouri in Columbia.
I have a presentation today to talk about applications and qualities of different NDE technologies for bridge deck inspections. And as Dave mentioned, I'm a professor at the university, and I also part-time partner in a company that does infrared technology. So I said as a disclaimer that one of the technologies in here is one that we developed through these pooled funds, and it's sort of in the wash with some of the other ones that are popular here. You know, the objective of this presentation was to try to describe the applications and qualities of NDE technologies, because there's been, over the years, a fair amount of confusion about what the different technologies do and how you might best apply them. And why would you pick one technology over another for a particular application? And one of them is we got started on was studying, GPR and what is this GPR results giving us. It's been used a long time. And if you look even in the most recent SHARP 2 report, you look at people that did GPR for them, right? The scales of the diagrams that are in there are very varied. One says the colors on this diagram mean serious, poor, fair, and good. The next one says it means probable delamination, probable corrosion damage. So those different descriptions make it sort of confusing what actually is being presented. So GPR is one of them. We'll show some images in here. IR is another one. Infrared, it's been grown in popularity recently. I hope to think that the pooled fund that we did with a bunch of states had something to do to contribute to that. What we studied a lot in the pooled fund was, what are the limitations of infrared? And it depends on the weather in order to get the driving function for how it finds defects. And so it's weather dependent, but it also depends on the depth and thickness of the defects. So depending on what you want to see in the bridge deck and how deep it might be, contributes to whether infrared's a good choice. Impact echo is a third technology not used as widely because it's kind of a point-by-point method. But if your basis of comparison is I want a technology that matches my chain drag, then impact echo is going to be almost perfect because physically they work on the same principles. And so looking at those three areas, my objective is just sort of describe what the differences are between those and the differences in how they work and how you might decide which one to use. It's sort of the fulcrums for NDE applications, a term I use here. What is it that makes the difference? And the real fulcrum is traffic control. Because if you close the bridge deck with traffic control, then really anything can be used. And you can use a hammer. So the benefit of your NDE technology in that case is only the delta between, if what you want to compare it to is hammer sounding, it's only the delta between hammer sounding and the quality of the NDE data, and it may not be that much. If you're not going to close the bridge and they're not going to use traffic control, then that's a different situation. And so that's really the fulcrum to make that decision. Another one is that there's a speed accuracy trade-off, and in visual inspection there's a thing called SATO. It's a speed accuracy trade-off. It's hard to be fast and good. Right, the faster you go, you tend to have lower quality of inspection results in visual inspection. And in some ways, it's similar with NDE technology. The desire to go very fast often leads to lower quality data. Another issue is whether or not you have an overlay and what type of overlay you might have. Do you have one that's going to interfere, for example, with acoustic technologies like an asphalt overlay, for example? What are the goals of your condition assessment? Another one is the goal to do something that's very highly accurate. You want to identify where on this bridge deck I need to make repairs. I want to be spatially accurate in terms of what its position is. Or do you just need some general idea of which bridges are prioritized over other bridges for some further evaluation? Well, those kind of lead you in different directions in terms of what NDE technology you might want to use. If you want to make a decision regarding, overlay, replace, or patch, maybe your NDE technology needs to be coupled with some of the other technologies that are available in some other inspections. Now, a lot of what this talk is sort of focused on is, well, if you wanted to detect delaminations in the deck, that's sort of the underlying assumption of some of my research. That's the objective of the research. And a couple things about delaminations in decks that a lot of them are caused by corrosion, but they're not all caused by corrosion. Sometimes you have delaminations and there's no corrosion involved at all. Sometimes you have corrosion, but you don't happen to have delamination. So it doesn't actually match one-to-one in all cases. Some damage in the bridge deck isn't a delamination at all. It's maybe some severe map cracking. So what kind of tools do you have for detecting delaminations? Well, hammer sounding, it can be kind of subjective. Normally requires traffic control. You have to get to the parts of the bridge that you want to inspect. You have to be able to touch. There's a variety of acoustic methods, and I'll talk about a few of them. Like hammer sounding, they require access to the surface. That's one of their limitations. Infrared thermography, having the advantage that you don't need access to the surface. You can do it from some distance away. And ground penetrating radar, well, does that detect delaminations we'll see some data about that. How do these NDE technologies work overall? Well, you know, none of them really detect defects. They produce signals, and there's variations in the signals that we relate or interpret to be defects. Now, there might be a lot of things that affect that signal, and if you just assume, well, any change in the signal is caused by a defect, right, you're probably going to be unsuccessful. And so you have to identify what the variations in those signals are, whatever the signal is, if it's an infrared signal or an attenuated signal from GPR or an acoustic signal in acoustic methods. How do you interpret that signal to identify that that is one caused by a defect as opposed to one caused by something else? And these are 10 things that can affect your signal, and you sort of make an optimistic assumption, well, it must be that one thing out of the 10 that I really want it to be because that's the one thing that's useful to me. And that can be, that sort of assumption can be, get you into trouble a lot of times. These threshold values are commonly used on some level or another. Now, there tends to be a lot of expert judgment mixed in with it, so there is threshold values, but then there's threshold values. There's sort of that in context with the expert judgment I've used, what other analysis I might have done to support that, and there's usually some subjective decisions before you get through the end of any NDE analysis. Now, there's some of these technologies that are more like survey methods, electrical methods for condition assessment, and they're NDE methods, but they're more for doing a survey of what the likelihood or potential for corrosion is, and a lot of them have been talked about here, and people are familiar with them. And I include them in this just to make a later point, but half-cell potential is a potential for active corrosion, resistivity, and galvanic static pulse, which is a polarization resistance measurement, and then there's a few different flavors of that one or different organizations of it into impedance. And these are all sort of survey methods. They don't detect damage directly. They detect maybe the potential for damage in terms of resistivity or the potential for active corrosion. And the thing to think that is important to know about all those things is that, you know, that if you look at the electrical properties of the material, and someone says, well, it's a change in the dielectric constant. Well, part of the dielectric constant is the conductivity of the material. In other words, the resistance, right? And so they said, well, I made a impedance measurement. It's not a resistance. Well, okay, impedance measurement is the resistance plus the reactance. So the resistance is part of the impedance measurement, and the conductance is the inverse of resistance. And so all those things are related. And so there's some really, I think, important diagrams in some old papers. This is just an example of resistance measurement off the internet somewhere. But this thing on the left here is really something that is worth looking at. It's got a kind of a classic paper, and on the vertical axis, it may be a little small to read, but is the resistance of concrete, and that's a log scale. So this is 10, this is 100, and this is 1,000. And on the horizontal axis is the moisture in the concrete. And on the right-hand side is 100% moisture content, and the left is the 40% moisture content, which is kind of the low end for concrete when you consider free water that's going to be in there. And so what the graph says is, well, my resistance changes 2 orders of magnitude just based on the moisture in the concrete. And so that's going to make it pretty difficult to make a quantitative measurement in an environment where the moisture is uncontrolled, like, for example, at a bridge deck. And so it challenges all those technologies because resistance is always part of them. And the moisture content is going to dominate that. And if you talk to, you know, inspectors, they're aware of that. They say, well, if it's really dry and I make a resistance measurement, I'm going to have very, very high resistance. Might have nothing to do with the corrosion susceptibility of my deck. It's because it's very, very dry that day. And if you wanted to make some long-term quantitative measurement, for example, the resistance would be a bad one to make because it's always going to depend on the moisture surrounding the bridge at the day you're there. In some specs, they identify resistivity as a measurement you should make on one deck, and it's relative to that deck. So it's one area of that deck relative to another. Because that's not the only thing that's going to affect the resistivity. So is the type of cement and the water-cement ratio. Those different lines are for different water-cement ratios. So there's a lot of variation there. The other graph here on the right is out of another old paper, and these guys took some concrete cubes and they measured them. And the horizontal axis here is in days. So this is 3,000 days, so about 10 years is this line here, right? And so these are concrete cubes stuck in different environments, and this one's in a controlled 80% humidity environment, and this one down here is in a fog environment. And so not only is there a big difference in the resistivity of the same material in 2 different environments, but over the life of the material it's changing. Okay, it's evolving over the life of the material. And then they got out to about 10 years, and I think they must have lost interest a little bit. I don't know, not sure what happens after 10 years. Okay, so a couple of the other technologies to talk about is a ground penetrating radar, and there's been a bunch of talks, so maybe we don't need to talk too much about it, but you know, it's an electromagnetic wave and it's reflected off the top layer of rebar. You make an assessment based on the amplitude generally of that wave or its velocity velocity represented by a change in time. So in areas that are damaged, it looks like it's delayed and the amplitude is lower. That's the underlying principle. And in terms of, and then you scan over the surface, so you scan along one line. I'll talk a little bit about how those images are generated. In infrared, you're measuring the radiant energy from the surface of the concrete. And the concept is that as it heats up during the day, this area above a delamination is going to heat up faster, and then the radiant energy is going to be greater. And it's proportional to about T to the fourth, so there's a lot of difference there. Now, that's a good example of, well, there's a lot of other things that can change that too. For example, if there's different colors on the deck. So there's different things that affect that signal. It's not just pure as it might be. So we look here at some studies we've done in different methods, acoustic methods, and I'll talk a little bit about the different flavors of them, infrared thermography and ground penetrating radar. So what are the flavors of acoustic methods? Well, there's a bunch of different ones. And sometimes it's hard to tell which one people are actually talking about. They got some very similar fundamental properties in that you've got to be able to hit the surface of the material consistently somehow and get that energy in. You got to get the energy back out. And you know, there's sounding and there's impact echo, and then there's seismic response, which is kind of like impact echo done by someone who doesn't want to call it impact echo. They would tell you differently, but I mean, there's only so much you can do with a wave. Surface acoustic waves, which is seismic response, bleed into that as well. I mean, those things are all pretty similar in a lot of ways. Seismic analysis of surface waves is really a different way to analyze the surface wave with a dispersion curve, trying to get properties through the thickness of a deck. But there's similar things are related to all these. One is that you got to make contact with the thing you want to inspect. And so you've got to touch the deck in order to do it. You've got to touch the concrete wall. You've got to have a surface that allows you to make a consistent impact and read back a consistent impact. If the surface is tined, you know, that might be a lot more challenges. If there's a thin asphalt overlay, well, are you going to be able to work through that? Well, maybe. You know, it depends on a lot of things, what your weight, your impactor is, what technology you're using. If it's a rigid overlay, you're going to see things under the overlay or just at the bond line. The disadvantage is it mostly requires lane closures. I mean, people have tried to develop and are trying to develop actively systems that you can drag along a deck at near traffic speeds. I think they're sort of drag along at a slower speed now because you create a lot of problems once you start bouncing along at 50 miles an hour. And they're point by point mostly, which means you have to touch the spot wherever you want to make a measurement, which means if you want to do your deck, you've got to close lanes. There's various implementations. Over the years, you know, here's an impact echo device that's a scanner. A couple people have shown these. Here's an acoustic wave device, which is being used it's actually part of an impact echo device. Here is a old cart with chains underneath it. And this technology of the chains underneath the cart thing has been around my entire career. So I think they first started in the 70s. It was a tool called the Lamtech. And you would, sort of looks like this, you drag it down the deck, and it had an electro-resistive printer on it, and a little pen would mark the paper when you got certain frequencies. And so this is, we always have a saying that it's research if it's new to me. And so my entire career there's been research to do this cart with the chains, but it's always been around too. So, and the bigger chains here, this is, I think, Shane's showed earlier on a slide. And so these are all implementations of that. What they share in common is that you have to be at the spot you want to evaluate. Okay, so there's different flavors of infrared technology. Most traditional ones are temperature anomalies at the surface of the deck are measured. This is handheld cameras. They can be vehicle-mounted bolometers, which is the handheld camera is typically a bolometer you mount on a car. You can drive it over the deck. Vehicle-mounted quantum detectors, which are more expensive equipment, but they can work at higher speeds. And then a newer technology, the one that we worked on through the pooled fund and the SBIRs, is ultra-time domain thermography. And that's a different type of measurement. It doesn't measure temperature, but it measures thermal inertia. And it's to address a couple of limitations of conventional infrared thermography, taking a time-lapse measurement. I'll show an example of that. Here's examples for conventional IR technologies. On the left is a handheld device. You look at it. The advantage of this is it's a real-time system, so you can have this camera in your hands and go to the field and see the delaminations right there and go out and hit them with a hammer if you need to, or figure out where on this bridge you maybe ought to access more or make a general assessment. Cameras cost about $20,000. It takes about a day to learn how to use them. If you take that camera, then you mount it on a truck and put it up at some height, either front or back, attach some sort of a spatial location device like an encoder. Then you drive over the bridge deck, you can make a plan view of the whole deck where it typically shows the visual image and the infrared image on the bottom. I'm going to run out of time talking about stuff if I don't hurry up here. So IR-UTD is a different animal. This is a place you put a camera up on a mast up above, or a light structure, or an ITS structure, or a sign structure nearby, up at a height of 30 feet or so, and then you're looking down on the top of the deck. You have a field of view like this. You can see across 5 or 6 lanes of traffic in a couple hundred feet in each direction, and it sits there and it collects data over 24 to 48 hours. You process that data not to find out what the temperature difference was, but the thermal inertia of the concrete over that time period. And you produce an image that looks like this. In this image, you see the girders that are beneath the deck, so you see through the deck. These are diaphragms beneath the deck, and that's damage that's subsurface in the deck. When it operates with all the lanes of traffic open, the vehicles are moved through data processing. And so from a one mass location, you get a piece of bridge deck that looks like this, looking to the left, looking to the right, and looking directly below. What's the challenge for conventional infrared is that defects change in shape and size over the course of the day. So if you start in the morning here, this is a temperature profile for a day. You start in the morning, later in the afternoon, you're going to get a bigger defect. Sometime in the day, it's going to disappear on you. And so it depends on the weather. Now, there's several flavors of GPR, vehicle mounted with 2 or 3 or more antennas, ground coupled, which is right on the surface of the deck, and here's like some sort of a hybrid they made in Kentucky of ground coupled radars attached to a vehicle. So talk a little bit about how that produces data, a GPR system. You drive down the deck. If you're doing ground coupled, let's say you're doing it every 2 feet, and you're getting a signal off of every rebar along the length of the deck. So if you were to look at those scan lines across this deck, well, it's not the whole deck, it's like every 2 feet. If you have fewer antennas, you have fewer data lines, and then that's put into a diagram that looks like this by interpolating in between the places where you actually have data. And so you sort of take this data in the field, and then you get these grayscale plots. You pick out where the rebars are, and you make this plot. Now, what we're doing is we're looking at a reliability of this through a receiver operator characteristic, which I'll explain a little bit, but in short order, this axis here is the probability of a false alarm. In other words, somewhere that's not defective is called defective. And the vertical axis is probability of detection. So it was called defective, and it actually was defective. So if you were a perfect technology, you would go all the way up this line. You'd detect something, and there'd be no false alarms. If you were travel along the 45-degree angle here, it'd be like flipping a coin, okay? 50-50 either way. I would make a plot here that shows probability of false alarm in red and probability of blue in the probability of detection as the reflection amplitude changes. All right, infrared, I think I already explained how that's provided, so running short of time. Wouldn't be complete without mentioning that effect of thresholds is significant in the NDE technologies, and this is where some subjective judgment usually is used. Here's 2 GPR scans of the same deck. It's the same data, but the threshold's set differently. So everywhere gray here is set to be sound concrete, and the green is the defective concrete. If I choose a threshold of -6 dB, I get about 43% of the deck recorded as damage. If I pick it as -8, I get about 22%. So it changes by a factor of 2, and that is the range in the ASTM spec that they say you should pick, between 6 and 8. Same is true for infrared. Conventional infrared, you've got some threshold where you're deciding this temperature profile indicates it's a defect. And so this is an infrared image, and superimposed on it is areas that exceed my threshold. Here's the temperature of a single pixel along a line that extends from the top of this picture down. And so I think, yeah, right, so it's the end of it's here. So if I set my threshold here, the only defect I detect is this, but I get no false calls. But if I set the defect down here, I get lots of false calls, okay? Lots of areas that look like they're defective that they aren't. Well, I've changed what my threshold was, okay? So that's part of the exercise. And so we analyze those thresholds in this way, okay? If the threshold's set very high, then I'm not gonna get anything except true positives over on this end. As I work towards this area, my threshold's reducing, and I'm getting more false positives. And along this curve, I'm sort of following this path, okay? I start out with all true positives, and eventually I get false negatives. So this curve is a way of analyzing the reliability of the technology. And the area under the curve is a measure of its reliability, without going too far from it. So we did some field tests on a couple of 3 bridges. We used for ground truth, we used impact echo, sounding by a team of people, and we took a borescope, we bored into the surface of the deck so we could see here's a picture of a delamination underneath the surface of a deck, to confirm that. Well, let's look at a couple of these quickly. Here's impact echo device. And see this curve? This curve indicates something that's pretty reliable, right? The probability of detection goes straight up, and then once your threshold gets kind of low, that does mix into some false alarms, but it's got an area under that curve about 95%. That's very good, okay? The problem is, see, this whole bridge deck, we've only done about 40 square feet of it because it took like 2 hours to do 40 square feet. And so if you have all the time in the world, that's going to give you a really, really highly accurate result. But you're going to have to close lanes, and you're going to be there for a couple days. And so that's the disadvantage of it. So how important is that to you? And what's the delta between what that tells you and what your chain drag told you? Okay? Now, the caveat is that, right, I'm measuring it against itself in a way. So it's almost circular logic. So I'm measuring it against chain drag and some sampling. Here's a couple of decks. There's a couple things I want to point out in here. Here's one of the decks. The dotted lines are the delaminations as identified by sounding and sampling and all that stuff that I just talked about. There's a couple of interesting things. Here's some bad patches here. This is the infrared image on top. This is conventional infrared. On the bottom is the GPR scan for a given threshold. You see here there's an area that doesn't seem to be in, that this threshold doesn't seem to be in the infrared data. You see the outline. But here it's a really strong response in the GPR data. Well, that's an area that's wet. And so because it's got so much moisture and it's not performing thermally like the rest of the deck, and that actually shows up as a negative area. So in the thermal, in terms of being a thermal anomaly, it's a negative anomaly. Here's another one, shows a similar thing. This area of the deck, it actually has water sitting on it. It rained a couple days before we ran the test. You don't really see a delamination in its natural form. I mean, there's indications there in the infrared, but there's indications in the GPR. The other thing you notice here is, I probably don't have time to make all these points, but there's delaminations there. This is the GPR scan here that don't appear at this threshold in the GPR data. But there's also areas where there's lots of delaminations that are sort of in the GPR area, right? Because it's showing areas where there's corrosive environment. And so there's delaminations in there. It doesn't measure them exactly because it doesn't measure them directly, but it measures that that area's got some corrosive environment in it. And in this case, it's resulted in delaminations. Now, if that corrosive environment showed up yesterday, it might not be delaminated yet. Or if it had showed up long, long ago, it might all be delaminated, right? So there's a difference in what's happening between those different technologies and how they're measuring stuff. And if you measure the reliability of that using this ROC approach, you get a little better for infrared than you do for GPR out of these decks. These decks were built in 1968 with black steel, and so they're sort of a prime candidates for this sort of conventional corrosion damage type damage in your bridge deck. One, it came out about 80 versus 68, and the other one's about 85 as opposed to 78. The reason of those differences is really the false calls, right? There's the areas that do not have delamination that are indicated as a defect following GPR. Now, it can be, you could make an argument that it's not the right comparison if you accept the argument that GPR is detecting the corrosive environment, not the delaminations. Then this doesn't make sense to even do it because it's not measuring delamination. But regardless, that was the purpose of the research. Here's an example of an IR-UTD result. This is, again, from a system that's mounted up on a mast, just to give you an illustration of that. This top figure here is IR-UTD data. The bottom is conventional IR. These are patches that appear in the surface of the deck. There's not much of a signal in conventional IR. There's a delamination signal here. The core is taken, it's this sort of nasty delamination at an angle. And that's a delamination that's not caused by, there's no corrosion in the deck. It's a delamination caused by either the fact there was some lightweight concrete used or there's too much flexibility in the deck. One more illustration of that technology here was sort of from a while ago, but to make a point that there's overlays, rigid or otherwise, challenge a lot of technologies. UTD is one of the purposes of it is to overcome that by looking at long periods of time. And this is what's in this image is IR-UTD results on the left, and then hammer sounding from the state of Iowa, done by Iowa DOT in the middle, and then an overlay of two on the right. So, last couple slides here, just in terms of these. This is a revamp of what I have just said in a sense. What are the speed qualities? Well, you know, GPR is really fast, air coupled because it's in with traffic. IR with quantum detectors maybe goes quick as that. Bolometers are next. Most of the acoustic auto systems, the ones you drag or push, are relatively slow. Maybe they're 10 or 15 miles an hour slower. You're pushing them along. Impact echo is quite slow, requires traffic control. The IR-UTD is kind of a different animal. I guess in speed, maybe you could look at it as not being that fast, but it's not interfering with traffic. The purpose of it is to give you accuracy. If you looked at these things in terms of impact on traffic, the sounding and impact echo are kind of on the right side, acoustics, some sort of infrared in the middle, and then IR-UTD, IR with a quantum detector, and GPR would be sort of on that end. So the final point would be the depth of damage, and that depends on different, varies for different technologies. Conventional infrared is relatively limited to 4 inches or less probably in your deck unless you have really optimum conditions. Impact echo sounding is also kind of shallow. It depends on who your sounder is. Some guys seem to do pretty good at 4 or 5 inches actually, but for the most part it's relatively limited to the top 4 inches. Impact echo can go deeper. UTD can go deeper because you can see through the full thickness of the deck over the time period, and GPR goes through the thickness for assessing corrosion. So, okay, so this is my conclusion slide. I'll finish up here that, you know, traffic impact I think is really the fulcrum of it, and what purpose of my study was just try to describe how these different technologies work and what affects them and how that affects your decision making and how important it is for you to either be accurate or to not disrupt traffic, and what is the relationship between speed and accuracy in some cases. Those are some additional conclusions I don't need to go over right now because they're too detailed, but I did want to leave time for a question. If you're interested in this reliability assessment in a more academic sense, to look at how that is done, there's 3 papers that are available, and you can get the slides or I'll give them to you. One is in TRB's most recent January meeting, and it'll be in the TRR later, but you could get it there now. One's in the Bridge Journal, one's in the International Journal for NDT, that explain how that reliability analysis is done and shows details of that data that I was showing.
I have one question. Like, you have used like ROC to determine the threshold of the results, right? So there's like one threshold. If we need to determine like multiple threshold, and instead of doing like good or bad, if I need to do good, poor, fair, severe, so can I use that technique to determine like if I need to determine more than one threshold in my data?
I don't know how to answer your question directly because I think I might need some more information about it. But yeah. I would just point out that, you know, you can set from this. These types of curves have all thresholds possible in them. So as you vary the threshold, the curve is developed. And so the best threshold is the one that lies closest to the 1-0 intercepts for that technology. Now this is based on a hit and miss approach. And so if you've got maybe missed, maybe hit, and missed, right, which is what you're saying.
Yes, exactly.
Yeah, I don't know. I mean, I guess you could bend that around to do something like that. At some point, it's a binary process of deciding whether it's a true positive or a false positive, true negative or a false negative. Okay, there are 4 options. And so now you've got times 4, I guess you'd have 8 or 16 options. So I'm not sure, but probably you could bend it around if you thought enough about it. But these are mostly, you know, geared towards a technology. So these curves came out of the medical field. And so a diagnosis, you're sick or you're not sick, and what the quality of that diagnosis can be. And it's normally coupled with or can be coupled with a confidence interval. And so I'm really sure you're sick, or I just think you're sick, right? And so maybe that's the approach. Maybe the approach if you want to do 4 is to look back at that way they approach that with 4 different decisions. I'm really sure of the decision, I'm sort of sure, I'm not so sure, and I'm sure negative. That might be a way to do it.
Of the states that you've done these trials on, how are they incorporating this into their program? Are they setting out routine contracts, or you know, how are they reserving their funding for these investigations?
Well, I don't know if I'd be the best person to answer that. So there's a couple of things going on here. With the conventional infrared technologies, we did that as a university study with MoDOT. Okay, so that data that I generated and showed images of was part of a university study with MoDOT. And so that was a couple bridges that were nearby to Columbia, and one of them was in Kansas City. And so that's an academic study in that part. The UTD stuff is normally done different ways, but it's kind of a unique technology, so we work a lot with consultants that have regular contracts with states. I know that just based on what I'm observing, you know, a lot of states are getting infrared and GPR scans through district contracts and things. I wouldn't know much about it. Ken would be a good guy to know. Ken would know all about that. Yeah. So, but the UTD is kind of a specialty thing. So it's normally done a lot of times with in cooperation with the consulting company that's doing a larger evaluation when you want to do something very accurate, or you've got a challenge like you've got overlays and things like that. So, thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.